Hi everybody, Denny here from ColdQuanta. Welcome to 3 Minutes of Quantum Computing. Today I'm going to finish developing the QUBO, which captures the StarBattle puzzle that we've been talking about. Last week we formulated the row, column, and region constraints as sub-QUBOs. Each of those constraints was a 1 of n, and we were able to handle all of them using a single trick. Today we need to convert the neighbor constraints into sub-QUBOs. For that we'll need something new, single-state penalty functions. A single-state penalty function is exactly what it sounds like. It penalizes one state out of a collection of states. It does that by assigning the value 0 to all states in the collection except for the penalized state, to which it assigns a positive value. Let's start with some simple examples. Suppose my state is described by a single variable, and I want that variable to turn off. That's the same as penalizing the on state. How do we do that? With a penalty function that equals 0 when our variable is 0 and positive when our variable is 1. A function which does this is simply equal to the variable itself. We call this a single-state penalty function because it penalizes exactly one state. If, instead, we want to turn the variable on, we must penalize the off state. We can do that with a slight modification of our function. Now, let's repeat this exercise for a state described by a pair of variables. In our first example, we want to penalize the state in which both variables are turned on. That's equivalent to saying that the other three states, the ones in which at least one variable is turned off, are all good. We can do that with a function that is simply the product of the two variables. For a two-variable problem there are 4 states, and so there will be 4 single-state penalty functions. Here is the entire set of them. And, as a further note, suppose that you really need to penalize more than one state. In that case, you can simply add together the single-state penalty functions which penalize the needed states. Here's an example where we penalize the two states in which the variables are not equal to each other. Now that we have mastered the single-state penalty function, let's go back and look at the neighbor constraint. Suppose x and y represent neighboring grid cells. Then we want to penalize configurations where there are stars in both the x and y cells. That's one of the two variable single-state penalty functions I just introduced. It's simply the product of x and y. That will penalize the configuration when there are neighboring stars, because that product will vanish whenever one or more of the cells is empty. When both cells have stars, the sub-QUBO will have a positive value. Armed with this new trick, all we need to do is apply it systematically to each potential pair of stars that violate the neighbor constraint. There are horizontal neighbors, there are vertical neighbors, there are diagonal neighbors like this, and there are diagonal neighbors like this. For each of those directions and for each neighbor pair with that orientation, we need to introduce single-state penalty functions to make sure that we don't get neighboring stars. Once we include all these penalty functions, we obtain the QUBO, which represents the entire StarBattle puzzle, by simply adding all the sub-QUBOs together. That's a lot of penalty functions, but we are going to write a Python program next week to handle the mechanics and spare ourselves a lot of pencil and paper work. That's it for today. Thanks for watching. Bye everybody.